Hey guys, so in this video, we're going to discuss Leetcode 729, which is a very frequently asked question in Google interviews. And in this problem, we're going to implement a calendar to see if we can book a meeting in the calendar or not. So let's look at an example. So in example one, what we can do is like initially the calendar is empty, like has nothing in it, and we're gonna check if we can book the meeting from 10 to 20 or not. Since the calendar is empty, there's no overlap with this meeting, right? Because it will be the first meeting, so we can just insert it into the calendar and mark it return true. And then we're gonna check if we can book from 15 to 25 or not, because there will be an overlap between 15 to 20. So we return false, and we will not insert this item into the array. And lastly, we're going to check if we can book 20 to 30 or not. And since there's no overlap, then we can just return true and book the meeting into the calendar. So in the calendar now, it will be like 10 to 20 and 20 to 30 will be all marked as booked. So the naive solution to solve this problem will be using an array. So every time we just have a order of n to look up every item to check if there's a duplicate, if there's an overlap between that item into my current booking, and then return a boolean. If no, we can just add the new booking into the array. So to improve the time complexity, we can use a binary tree. So what we can do is like if the booking is purely random, then on average, the tree will be a balanced tree. And if the tree is a balanced tree, the height of the tree would be order of log n. So the lookup would be like the lookup in the binary tree would be time of log n. So we can just like search through the tree to see if the time has any overlap with any item in the tree or not. And then like if there's no overlap, we can just insert the node into the tree, and the insertion will be just order of one complexity. Like inserting a node in the binary tree will be order of one. So yeah, so let's try to code it out. So we can create a new class in this solution, like call it a node. So this will be every node in the tree. Maybe we can have a better name. Maybe call it book, booking, book item. So it will have a start time and the end time. So, and then we can just initialize it. Sorry, I need to remove it here. Sorry for the syntax issue. So we have a start time and end time, so we can have like every booking will have a start time and the end time. And then it will have the left child and the right child. So initialize it to 0, to now, sorry, not 0, self dot right. No. So for the left child, it will be every book meeting will have a ending time smaller than the starting time, current starting time. And on the right child, so all the meetings on the right hand side would be having a starting time larger than my current node's ending time. All right, so now we can initialize the calendar. So initialize calendar would be initialize self.root would be a none. So which means the calendar is empty. So if we wanna, and now we're gonna book the node. So the new book, let me just properly make it uppercase. So new book will be a book item of the start time and end time, right? So if not self.root, so if the calendar is currently empty, then we can just initialize the root as a new book. We initialize the current book as the root of the calendar, and we just return true, which means we can put the new book inside of the calendar. Otherwise, we can just what we can do is like we can check if the new book can be inserted into the tree or not. If not, we return false. Otherwise, we return true. So we can what we can do is like self.root. We can implement a new function here. What we can do is call it insert. So every node can insert. self and insert a node, let's say insert an item, insert a book item. So what it does is like, let me pause it here. So what it does is like, so check if it can add child to item as a child to current node and return a boolean. And we can just simply return boolean here. So we can just self.root insert the new book. We can return it here because we return the boolean in this function, so we can just return. So it will either return true and insert the new book as a child in the tree, as a node in the tree, or it will return false. All right, so there will be several cases here. So either if the item, the starting time is larger than equal to the self, if the start time is larger than the end time, then what we can do here is like invert to the if the start time, if the new node start time is larger than ended, then we can invert to the right. All right, let me define all the cases if item dot end time is smaller than self dot start time. Then in this case, we if the end time we insert to the left. Otherwise, there means sorry, my bad. Otherwise, it means there's an overlap, so we just return false. All right, so let's check to the right. So there will be several cases, like if self right, if there's no right, if not, if the right doesn't exist, right? Let me put a comment here. If the right node doesn't exist, what we can do is like we can simply self insert the node to the right, self the right equals item and the return true, because we can insert it. Otherwise, we can just do it recursively to check the self right insert the item. We just call it recursive to check if the right node can insert the item or not. And we're gonna do the same for the left. Yep, if not left, and I think should work. Let's run and see how it goes. Oh, runtime error. If not, oh, sorry, missed it. Semicolon here. Oh, and same here. Yeah, it works. So yeah, so as I have mentioned before, the time complexity value will be order of log n, because we're gonna do a log n to lookup, and for the lookup and order of 1 to insert, because this is the insert. And for the space complexity wise, it will be order of n for all the n time slots for the booking. So yeah, this is the end of the video, and I'll see you guys in the next one.